Howdy and welcome. This is a video based on the textbook First Course in Mathematical Logic by Patrick Suppes and Shirley Hill. We're on Chapter 3, Truth and Validity, Section 3.1, Introduction, Section 3.2, Truth Value and Truth Functional Connectives. Let's begin. The Section 3.1, there's only one slide here for this section. Now in logic, we can prove if a valid conclusion actually derives from given premises. An argument is valid if it can be supported by a rule of inference. We've covered several of them. For example, there's modus ponens, modus tollens, we have hypothetical syllogisms, constructive dilemmas, and so forth. Now, if we have true premises and we have a valid argument, then we know we actually have a true conclusion. If we have a valid argument, we know we have a valid conclusion, but the truth or falsity of the conclusion is left open because we would have to know if the premises are in fact true. So a valid argument only means a valid conclusion. Now, if we know a valid conclusion is in fact false, however, then at least one premise must be false. Similarly, just because we have true premises and a true conclusion doesn't mean the argument was in fact valid. Now, there may be valid inferences that are not listed in our rules of inference. So we have to be able to prove if it's valid or not. We might be able to derive it from our list. In that case, it's valid. So we can use the rules of inference we already have to derive, so to speak, a new rule of inference and show that it is in fact valid. Now, this chapter will introduce us to new techniques to find out if a certain rule of inference is in fact valid that's not already proved by our previous videos. Section 3.2, which is going to be what the rest of the video is on, deals with truth value and truth functional connectives. Each sentence has a truth value. A truth value is either true or false exclusively. That is, either one or the other. If it was both, of course, we would violate the law of contradiction. Knowing the truth values of the atomic sentences of a molecular sentence and how they relate to each other by sentential connectives allows us to know the truth value of the molecular sentence. For example, as we'll see in the next slide, if we have a conjunction such as P and Q, if we know that P is in fact false, then of course this molecular sentence is false. Okay. So by knowing the atomic sentences, knowing if they're true or false, we could then figure out what the truth value of the whole molecular sentence is. So as I was saying, we have the conjunction P and Q. Both atomic sentences, P, Q, must be true for this molecular sentence to be true. By the way, this is mentioned in the textbook, so I might as well mention here as well. There's no need that P's subject matter have anything to do with Q's subject matter. They could be totally unrelated. All that matters is that the conjunction is true if and only if both the atomic sentences are true. Now, how many truth values are possible here? So P can either be true or false, and Q can either be true or false. So there's 4 possibilities. Of course, 2 times 2 is 4. So P can be true, Q can be true, or P is true, Q is false, or P is false, Q is true, or P is false, Q is false. And as we know, P and Q is true if and only if P is true and Q is true. So only one option of the 4 will make the molecular sentence true, whereas the other possibilities will make it false. The next molecular sentence is a negation, not P. So P has 2 possible truth values, true or false. So if we have a true P, so we'll say P, and I'll say that's true, then its negation must be false. So if I say Russell Kirk was an author, and that's true, and then I say it is not the case that Russell Kirk was an author, that must be false. And if we have the negation of a false P, we have something that's true. So if P is false, then its negation must be true. Next up is a disjunction. So our molecular sentence is P or Q. And remember, the or is inclusive, so both options can be true. P can be true, Q can be true, or both P and Q can be true. How many truth values are possible here? Well, there must be 4 because we have 2 atomic sentences, and obviously 2 times 2 is 4. So for the disjunction to be true, at least one option must be true. So for example, either I will eat bacon or eggs. If I eat neither, then the statement is obviously false. But if I eat one, it's true. And if I eat both, it's true. So if we look through our options, we see this option, and this option, because you have one true atomic sentence, makes a molecular sentence as a whole true. Whereas the last one, P is false and Q is false, will of course make the molecular disjunction false. Next up is our conditional, if P then Q, or P implies Q. How many truth values are possible here? Again, there are 4, as there are only 2 atomic sentences. Here's an example. If it rains, then the game is off. It rains is the antecedent, that's P. The game is off is the consequent, that's Q. The first 2 truth value combinations are pretty straightforward, they're pretty easy. The last 2 are a little bit confusing. So let's say it's raining, that's true. The game is off, that's true. So it's raining and the game is off. Experience has vindicated this conditional. It hasn't falsified it. We have no contradiction to that conditional, and so it's a true conditional. On the other hand, let's say it does rain, the antecedent is true, but the game is not off, so the consequent is false. Experience has falsified this conditional. We have contradictory evidence, so it's definitely a false conditional. But here things get a little bit confusing because the next 2 we call vacuously true. So it rains is false, the game is off is true. We will consider this a true conditional, or perhaps better put, we call this vacuously true. We might think of it this way. First off, remember that the antecedent is only sufficient for the consequent. It's not necessary for the consequent. So the game might be off for another reason. So just because it's not raining, the game still can be off. So we can say that experience has not falsified that conditional, and because it has not falsified it, we will just treat it or stipulate it as vacuously true. Likewise, it rains, false, the game is off, false. We will call that vacuously true. So let's say it's not raining, and the game is on. So we haven't falsified that conditional, we'll treat it as vacuously true. So these 2 are vacuously true. I should note a few things here. Another reason why these 2 we consider vacuously true, that in mathematical logic we have this truth functional point of view. And we stipulate that if P then Q is logically equivalent to not P or Q. So if this holds, if this left-hand side is logically equivalent to this right-hand side, and remember in a disjunction, in mathematical logic, it's inclusive, so not P and Q can both be true. And if that's the case, we have to treat these last 2 conditionals as vacuously true. All that matters in this truth functional logic is really the combinations of true and false. There's no necessary, so to speak, link between the antecedent and the consequent. The antecedent does not have to be the cause of the consequent, for example. They could be totally unrelated. So truth functional conditionals are strictly speaking different than, let's say, ordinary language conditionals. They are different. I can't hand wave this problem away. Some people do, but they are definitely different. So if I say if 2 plus 2 is equal to 4, then Jupiter is a planet. The antecedent and the consequent have nothing to do with each other. But we'll say that's true because we have a true antecedent and true consequent. Okay? So that's important to note. The truth functional conditional is not very strict because we have only one possibility of a false conditional when you have a true antecedent and a false consequent. Otherwise, you have a true conditional. And finally, we have biconditional sentences. These are equivalencies, P if and only if Q. And in truth functional logic, an equivalency holds if P and Q have the same exact truth values. So P has the same truth values as Q. And likewise, Q has same truth values as P. So it's very important. We might also say that P is both sufficient and necessary for Q, and Q is both sufficient and necessary for P. And of course, there are 4 truth values possible here. Here's an example on page 117 of the Supplemental textbook. You are permitted to vote if and only if you are registered. First possibility. You are permitted to vote. True. You are registered. True. They have the same exact truth value, so it's definitely a true biconditional. You're permitted to vote if and only if you are registered. So for that to be true, one possibility is both P and Q are simultaneously true. How about this? You're permitted to vote. True. If and only if you're registered. False. Clearly we have false biconditional because they don't have the same values. You're permitted to vote. False. If and only if you're registered. True. Once again, we have something that's false. On the other hand, you're permitted to vote. False. If and only if you're registered. False. So we're going to treat this as true. After all, we have P and Q having the same exact truth values. Both are false. So in a biconditional, P if and only if Q, that statement is true only when there's a logical equivalency between P and Q. They're both simultaneously true or both simultaneously false. Let's work on exercise 4C from pages 116 to 117. So we're to tell whether if R then not S is true or false in each of the following cases. Number 1 tells us that R and S are both false. The only thing that's a little bit confusing is that in the consequent we have a negation. So you have to really keep that in mind. The negatives and double negatives, those sorts of things, always make things a little bit tricky. We can think of it this way. We can say R is false implies a truth. Okay, so S is false, so not S is true. So if the consequent is true, then the overall conditional must be true. So number 1 is in fact true. Number 2, R and S are both true. So we have truth implies falsity. So overall, that must be false. So if the consequent is false and the antecedent is true, then we've falsified that conditional. So it's definitely a false statement. Number 3, R is true and S is false. So we have truth implies truth. Well, both antecedent and consequent are true, so the conditional is true. Number 4, R is false, S is true. So we have false, arrow, false. So both the antecedent and consequent are false, so the conditional is true. Exercise 3B from page 114. Tell whether not R or not S is true or false in each of the following cases. And in disjunction, of course, you have to have at least one of the choices as true. And what's a little bit tricky, of course, is that negation, that negative sign. So we have, for 1, we have R is true and S is true. So let's just, so to speak, translate that into that that sentence. So we would have false or false. So the statement must be false because neither option is true. Number 2, R is false and S is true. So we have truth or false. So one of them is in fact true, so that's a true statement. Number 3, R is true and S is false, so we have false or true. One of them is true, so the molecular sentence is in fact true. Number 4, R is false, S is false, so we have true or true. So the statement is true. Number 5, R and S are true. So we have false or false. Well, nothing is true, so it must be false. 2 more exercises to go. Exercise 2A from page 113. Tell whether P and not Q is true or false in each of the following cases. Number 1 tells us that P is false and Q is true. And in a conjunction, for a conjunction to be true, each of its conjuncts must be true. And notice that Q and not Q are definitely contradictories of each other. So P is false, and well, Q is true, so not Q must be false. So neither option is true, so the statement as a whole must be false. Number 2 tells us that P is true and Q is false. So we have true and true. Well, both statements are true, so the statement as a whole must be true. Number 3, both P and Q are true. So we have true and false. Well, there is a falsity there, so the molecular sentence must be false. Number 4, P and Q are false. So we have false and true, but one of those is false, so the molecular sentence is false. Number 5, P is true and not Q is true. Well, so both conjuncts are true, so therefore the sentence as a whole is true. Finally, exercise 1A from page 112. Jack says, my birthday is in August and Jane's is in the following month. We find that his birthday is in August, but that he was mistaken about Jane's birthday because it is in November. Is Jack's sentence a true or false one? Can you explain your answer in terms of the rules of uses for conjunction? Well, it must be a false statement because we have a conjunction and one of his conjuncts is false, namely this Q. So the molecular sentence must be false. And that's it for this video. Up next is section 3.3, diagrams of truth value. I'll see you soon. Thanks so much for watching.